We live around a star, our sun. It's a pretty standard yellow dwarf star. It's stable. It gives us light and heat in reliable doses. Life on Earth is built around this predictable cycle of energy. It's day and night, summer and winter. The sun is the engine of our world. It's so fundamental we don't even think about it. But what if we didn't have a sun? What if instead our solar system was centered on something else? Something more exotic, something more violent. Could we live around a pulsar? First, we need to be clear about what a pulsar is. It's not a star, not in the way our sun is. A star is a giant, ongoing nuclear fusion reaction. It burns hydrogen into helium, releasing tremendous amounts of energy as light and heat. A pulsar is what's left over when a massive star dies. It's the corpse. When a star much bigger than our sun runs out of fuel, it can't support its own weight anymore. The core collapses in on itself in a fraction of a second. The outer layers rebound off this super dense core and explode outward in a supernova. It's one of the most violent events in the universe. What's left behind at the center is a neutron star. A neutron star is one of the strangest objects imaginable. Imagine taking a star 1.5 times the mass of our sun and crushing it down into a sphere maybe 12 miles across. The size of a city. The gravity is so intense that it smashes atoms to pieces. Protons and electrons are forced together to become neutrons. It's a giant ball of pure nuclear matter. A single teaspoon of it would weigh billions of tons. A pulsar is a special kind of neutron star. It's one that spins, and it spins incredibly fast. The original star had some rotation, and just like an ice skater pulling their arms in to spin faster, the collapsing core spins up to insane speeds. Some pulsars rotate hundreds of times every second. This spinning, super dense object has an immensely powerful magnetic field. Trillions of times stronger than Earth's. This magnetic field channels particles and shoots them out from the magnetic poles in two tight beams of intense radiation. X-rays, gamma rays, all sorts of high energy stuff. Because the magnetic poles are not aligned with the spin axis, these beams sweep around the sky like the beam from a lighthouse. If you happen to be in the path of one of these beams, you see a pulse of radiation every time it sweeps past. That's why we call them pulsars. We are seeing the pulse of the cosmic lighthouse. So, could we live around one of these things? Let's be honest from the start. The answer is almost certainly no. Not for life as we know it. The environment around a pulsar is one of the most hostile places in the universe. It's a laundry list of ways to die, but exploring why it's so bad helps us understand our own place in the cosmos. And it lets us imagine what it would take for some hypothetical, super advanced civilization to even try. The first and most obvious problem is the radiation. Those beams are not gentle, life-giving light. They are death rays, they are torrents of high-energy particles and radiation that would sterilize a planet in an instant. If Earth were orbiting a pulsar in the path of one of its beams, our atmosphere would be stripped away. The surface would be scoured clean. Any life would be vaporized. An atmosphere, even a thick one, wouldn't be enough protection. The gamma rays and X-rays are so powerful they would punch right through and shred the DNA of any living thing. There's no sunscreen for this. You would need shielding. Not just a little bit of shielding, but miles of solid rock or lead to even begin to feel safe. Life on the surface would be impossible. You'd have to live deep underground or in the depths of a very, very deep ocean. Even then, the planet itself would be in trouble. The constant bombardment of radiation would change the chemistry of the atmosphere and the surface. It wouldn't be a stable place for life to get started in the first place. This brings us to the next problem, the habitable zone. For a star like our sun, the habitable zone, or Goldilocks zone, is the orbital distance where a planet could have liquid water on its surface. Not too hot, not too cold. The sun provides a steady output of light and heat, so this zone is a relatively stable band of space. A pulsar doesn't work that way. It doesn't produce much heat or visible light. It's a dying ember, not a roaring fire. Most of its energy output is in those focused beams of lethal radiation. So, if you wanted to get warm enough for liquid water, you'd have to orbit very close to the pulsar. But orbiting close means you are deep inside the radiation kill zone. The place that's warm enough to melt ice is also the place that will strip your atoms apart. There is no Goldilocks zone around a pulsar, there's just the cold, empty zone and the instant death zone. They are basically the same place. The very energy that would warm you is the same energy that would kill you. It's a fundamental contradiction. You can't have one without the other. But let's say you could somehow solve the radiation problem. Maybe your planet has a magical, impenetrable shield. You still have another massive hurdle. The magnetic field. The magnetic fields of pulsars are beyond human comprehension. Earth has a magnetic field that protects us from the solar wind. You can see its effects in the aurora. A refrigerator magnet is stronger. A hospital MRI machine has a very strong magnetic field. A pulsar's magnetic field is 1,000,000,000 times stronger than the strongest magnet humans have ever built. At that strength, the laws of chemistry begin to break down. An atom is a nucleus with electrons orbiting it. In a field that's strong, atoms themselves get squeezed and distorted into long, thin needles. The way atoms bond to form molecules would be completely different. The chemistry that life on Earth depends on, based on carbon, water, and complex organic molecules, would be impossible. The very building blocks of life would be torn apart or forced into bizarre configurations. Your body is a collection of complex chemical reactions. In that magnetic field, those reactions would stop. Its electronics would be useless. A compass would not just point north, it would be ripped apart at a subatomic level. It's not an environment, it's a physical reality, so alien that our understanding of matter itself starts to fray at the edges. You would have to be very, very far away from the pulsar for the magnetic field to weaken to a point where normal chemistry could even occur. And by then, you'd be in the deep freeze of interstellar space. Okay, let's keep pushing this thought experiment. Let's say you have a shielded planet, far enough away that the magnetic field is manageable. You still have to deal with gravity. A neutron star is incredibly dense. That means its gravitational pull is immense. A planet orbiting a pulsar would experience extreme tidal forces. The side of the planet closer to the pulsar would be pulled much more strongly than the far side. This stretching force could be enough to rip the planet apart if it gets too close. This point of no return is called the Roche limit, so any habitable planet would have to orbit safely outside this limit. Even if the planet survives, the tidal forces would have dramatic effects. They would knead the planet's interior, generating immense heat through friction. This could lead to runaway volcanism, turning the surface into a molten hellscape. Or, if the planet is an ice world, it could create a subsurface ocean of liquid water, which is an interesting possibility for life. But it would be a violent, unstable world. Then there's the nature of the energy source itself. The pulsar's beams are not constant. They blink. You get a blast of energy, then nothing, then a blast, then nothing. This happens hundreds of times a second. Life on Earth evolved to use a steady stream of sunlight. Plants use photosynthesis to slowly store energy over the course of a day. The pulsar day would be a millisecond of lethal radiation, followed by a night of absolute cold. There's no way for life to adapt to that. How could a plant evolve to capture an instantaneous blast of gamma rays? It would be like trying to drink from a fire hose that's also on fire and shoots bullets. The energy is not only in the wrong form, high energy radiation versus gentle light, but it's delivered in the worst possible way, brief, violent pulses. This makes it useless as a direct energy source for life, and we haven't even talked about where the pulsar came from. It was born in a supernova. That means the entire region of space around it is a chaotic mess. It's filled with gas, dust, and the debris from the exploded star, all moving at high speeds. It's not a clean, orderly place like our solar system. Finding a stable, long-term orbit for a planet in such a chaotic environment would be difficult. The neighborhood is just too rough. So, for life as we know it, it's a non-starter. You're irradiated, frozen, ripped apart by magnetism, stretched by gravity, and living in a cosmic war zone. It's hard to imagine a worse place to set up a home. But the question was, could we live around a pulsar? Not could life like us naturally evolve there? That's a different problem. Let's imagine a civilization far beyond our own. It's a civilization that can move planets, build megastructures, and manipulate the laws of physics in ways we can only dream of. How would they do it? First, they'd have to solve the radiation problem. Living on a planet's surface is out. Living underground is a better idea. A planet with an extremely thick atmosphere and a deep ocean could provide the necessary shielding. Perhaps they could live in mobile habitats deep in the global ocean, protected by miles of water. But there's a more elegant solution. What if you just avoided the beams? The beams shoot out from the magnetic poles. If you could place a planet in an orbit that is perfectly aligned with the pulsar's equator, the beams would always pass over the planet's north and south poles. You'd never be directly in the line of fire. It would be like living next to a lighthouse, but staying out of its beam. The sky would have two terrifyingly bright spots sweeping across the heavens, but they would never point directly at you. This is a clever trick. It completely removes the primary danger. You'd still have to deal with some scattered radiation from the pulsar's magnetosphere, but the main death rays would be avoided. This solves one problem but creates another. If you're avoiding the beams, you're also avoiding the main source of energy. The pulsar itself is not very hot. It's cooling down over billions of years. So a planet in this special safe orbit would be frozen solid. How do you get heat and power? This is where the tidal forces we talked about earlier could be an asset instead of a liability. A large planet, or a planet with a large moon, orbiting the pulsar would be constantly squeezed and stretched by the intense gravity. This tidal fluxing would generate enormous heat in the planet's core. It would be a world powered by geothermal energy on an unbelievable scale. Constant volcanism, hot springs, and a warm subsurface would be the norm. So you could have a planet, perhaps an ice giant with a rocky core, orbiting the pulsar in the equatorial plane. On the outside, it's a ball of ice. But deep beneath the frozen surface, thanks to tidal heating, there's a vast ocean of liquid water. Here, shielded from the ambient radiation by miles of ice, life could exist. Not life powered by a sun, but life powered by the heat coming from the planet's own core. They would live in eternal darkness, clustered around hydrothermal vents, much like the strange creatures in Earth's deep sea trenches. For an advanced civilization, they wouldn't need to rely on passive geothermal energy. They could harness it directly. They could build power plants that tap into this immense source of tidal energy. They would have a virtually unlimited power supply as long as their planet kept orbiting the pulsar. What about the magnetic field? The only real solution is distance. You have to be far enough away for the field to weaken to safe levels. This works well with the tidal heating model, as you don't need to be close to the pulsar for warmth. The gravity is what provides the heat, and gravity has a very long reach, so we can start to piece together a plausible, if extreme, scenario. An advanced civilization finds a rogue planet or moves one into position. They place it in a stable orbit around a pulsar's equator, carefully avoiding the deadly radiation beams. The planet is large enough that the pulsar's gravity constantly churns its interior, creating a permanent source of geothermal energy. The civilization lives in cities deep underground or under a thick ice shell, tapping this energy for power. They would have a stable, long-term home. What would it be like to live there? The sky would be black, dotted with the familiar stars, but it would be dominated by the pulsar. You wouldn't see the pulsar itself, as it's tiny and not very bright in visible light. But you would see the effects of its beams. Twice per rotation, hundreds of times a second, two impossibly bright searchlights would slash across the cosmos. They would illuminate the nebulae and dust clouds in the surrounding space, causing them to glow in an eerie, strobing display. It would be a silent, terrifyingly beautiful light show in the heavens, a constant reminder of the cosmic monster you call your sun. There would be no day or night in the traditional sense, just the eternal darkness of the deep, punctuated by the rhythmic flicker of the pulsar's beams on the clouds above. Society would run on its own clocks. Agriculture would be impossible. All food would have to be grown artificially, perhaps using hydroponics and aquaponics powered by geothermal or fusion energy. The pulsar itself would be an object of intense study. Its regular pulses provide a clock of almost perfect precision. Navigating by it would be simple. It would be the ultimate cosmic metronome. But it would also be a source of constant danger. A small wobble in the pulsar's spin, a starquake on its crust, could slightly alter the direction of the beams. The civilization would need constant monitoring and the ability to adjust their planet's orbit to stay in the safe zone. It would be a life of high-tech vigilance. What about the raw materials? A supernova remnant is a messy place, but it's also rich in heavy elements. The explosion that created the pulsar would have seeded the surrounding area with all the elements on the periodic table. Asteroids and comets in the system would be rich mining opportunities. The civilization would not want for resources. So, could we live there? Humans, as we are now? Absolutely not. We are fragile creatures of sunlight and stable gravity. We belong on the quiet plains of the G-type star's solar system. But for a hypothetical species that evolved for such a life, or for a technological civilization capable of planetary engineering, it's a fascinating possibility. They would be a culture shaped by darkness, pressure, and immense power. Their science would be deeply intertwined with gravity and high-energy physics. Their mythology would be built around the strobing eye in their sky. This whole thought experiment does something important. It highlights just how special our own situation is. We complain about the weather, but we live on a planetary paradise. Our sun is a gentle, stable source of energy. It doesn't try to kill us with gamma rays. Our planet's magnetic field is just strong enough to protect us without scrambling our atoms. Our orbit is stable. Our neighborhood is quiet. Life on Earth is possible because of a long list of fortunate coincidences. We are in the right kind of galaxy orbiting the right kind of star at just the right distance. It's easy to take that for granted. Imagining life around a pulsar forces us to confront the alternative. The universe is not, by and large, a friendly place. It is filled with violence, radiation, and extremes of temperature and gravity that are hostile to the delicate chemistry of life. Places like Earth are the exception, not the rule. So while a pulsar system would be a terrible place to live, it's a wonderful place to think about. It shows us the boundaries of what might be possible, and it reminds us to appreciate the calm, boring, life-giving star we call the sun. It's good to have a normal star. It's good to have a home that isn't actively trying to erase you from existence hundreds of times a second.